Good afternoon, everyone. Welcome to our panel, Connecting Quantum Domains for Scale. I am Panagiotis Spentzouris. I am the Associate Lab Director of Emerging Technologies at Fermilab. In this panel, we're going to discuss what happens as our quantum systems evolve, as you've been hearing actually all morning and afternoon until now in this event. And as I'm sure you're very aware, we're reaching the point of maturity that individual breakthroughs at each individual platform or approach are not enough at this point. We have to consider how we put all that together to build something larger to be able to achieve the full potential of the technology. So today we're joined by our three panelists that are at the heart of this challenge. Kelsey Ortiz from Photon, Jordan Shapiro from IonQ, and Jonah from Xanadu. Kelsey is a PhD student at UIUC, where she works on developing quantum space payloads. In addition to her academic research, she's a co-founder of Photon, a startup emerging from Paul Kwiat's group. The company is developing deployable optical delay quantum memory to support both photonic quantum computing and quantum networking. Jordan is the president and general manager of quantum networking and sensing at IonQ, and he's local. He's from Chicago. Previously, he served as IonQ's vice president of financial planning and analysis and corporate development and investor relations. And before IonQ, he was a technology investor at NEA, one of the world's largest and most active venture capital firms. Finally, Jonah is the director of government relations at Xanadu, a leading quantum computing hardware and software company, full stack. Previously, he served as director for cyber and emerging technology at the National Security Council staff at the White House, where he led presidential initiatives on a range of emerging technologies. So together, we're going to explore what it takes to achieve scale. And I will kick off with one most general question following my introduction. Each one of you represents a different platform. And not only that, but you represent companies at different stages of their evolution. Xanadu is a full stack photonic quantum computing company that was just announced that it will be trading publicly pretty soon. IonQ is already trading publicly. It started as a trapped ion quantum computing company, but in the process of its scaling up, no pun intended, it has acquired both sensing and I think two quantum networking related companies. And then Kelsey represents a true startup that is at the beginning of its arc towards scaling. So how do you see these domains and these platforms, different platforms that you represent, coming together as we move towards scalable quantum systems? How each one of you views their role in scaling up, scaling the ecosystem? Well, let's start to my, my left. So Jonah, you go first.
Sure. So, each of the different platforms takes a very different approach. But what I'll say is there are a lot of commonalities between them in terms of the kinds of materials, the kinds of manufacturing processes, the kinds of training and workforce development programs that you need, right? So at this point, there is sufficient space in that Venn diagram of things that we all need and things that benefit all of us, right? So we're at sort of that pre-competitive stage in the industry where rising tide lifts all boats, right? We want to see more investment. We want to see more attention from governments. We want to see more attention from students, right? And you really need all of those things to come together to see a industry that becomes fully commercialized, right? So customers are essential. Workforce and expertise is essential. Developments and innovations in one area of the industry can have spillover effects into others. So, I think we're still at a point where as these technologies mature, it's going to be collective advancement. And then, in a few years, I think we're going to start to see a bit of a winnowing of the industry, and you'll start to see some market leaders that really push things forward. But right now, it's about building that groundswell of energy to really push the industry into the next phase.
IonQ is a full quantum technology company spanning from the quantum computers, the quantum networks, sensors, security, quantum security. And when you're a company that is looking across the industry broadly, you realize there's no way to do this alone. There's no way to just be a single company in a space because there's everything from the government to the workforce development, like Jonah mentioned, also the supply chain development. And so what you tend to see is that as quantum has developed over time as an industry, truly that tide raising all ships mentality applies to the industry. And the resources become more and more available for each other. Take, for example, this conference and the venue and the people who are congregating about quantum worldwide. And that has changed remarkably versus 5 years ago, versus 10 years ago. I'm very excited to see how we continue to raise each other's tides, raise each other's ships in the 5 and 10 years to come.
Great. Yeah, so just to reiterate, I'm from PhotonQ, so we're making optical delay line quantum memories, basically reflection cells. So one could say it's the simplest kind of memory, but also the most efficient and the most useful right now. And it could also connect different qubit modalities. So no matter what qubit modality you have, you're always going to want to network with photons, right? And that's where we would play in, and we're broad bandwidth, so we'd be able to work with different qubit modalities. So we're hoping to connect different quantum companies and work with different quantum companies. I would say also it's a great time to be a startup right now in this ecosystem. There's a lot of excitement happening right now. And this has given us the opportunity to really get involved in this community and really make a difference as an early stage startup, start getting customers and start making a footprint in this ecosystem.
Thank you. So Tide lifts all, not just on the technology, but also the success that the more mature companies have viewed from a startup at its first stages of evolution, which is good. And actually, that was a good segue having you talk last, because I'm going to start with you talking first and asking the following question, which is interoperability is a big challenge for actually achieving the goal of scaling. So what do we need, technically or organizationally, to make different platforms talk to each other? Is it just the technology? What is your view? Starting with you.
Yeah, so I would say specifically for PhotonQ, in terms of scaling up, our systems are bulk optics. That's what makes our system most efficient and most special. But with that, obviously, you would want to be selling hundreds of these to quantum companies. And so that's a challenge for us, at least, is to figure out how to scale our technology down. And that becomes an engineering problem, right, which requires different fields and people from different fields, scaling it down size-wise, but also thinking about power considerations. So it really requires people from different areas, I would say, versus transitioning from like working in our research lab where we just focus on the physics and none of the engineering problems. I think for the future, we need to start incorporating all those kind of people in our work. And yeah, I guess I will just say, like, for PhotonQ, right now we are 4 co-founders and we are trying to grow. So we are looking for people. So if you are a student with an engineering degree, optical engineering, electrical engineering, I would love to chat afterwards. But yeah.
Certainly a take on interoperability is getting more people to interoperate with, right? So at IonQ, the way that we think about quantum networking is that we're building a platform that should scale not just for ourselves, but for the entire industry. And similarly to what Kelsey mentioned, we're thinking about taking kind of earlier stage devices and always pushing the envelope on getting those to commercial scale. And today I'm excited to say that we have done that. We have commercial scale quantum networking equipment, and we're always focused on the next version of it. But what does it mean to interoperate truly across the ecosystem? we think there are a series of quantum devices that you must have that IonQ is building today. So take, for example, quantum frequency converters. These are devices that take a frequency from one quantum computer, one quantum device. It operates at a certain wavelength of light and changes those into a standard wavelength that can operate on telecom. We announced in September that we'd achieved a demonstration of that with the Air Force, one of our customers, the Air Force Research Lab. So these frequency converters are key to allowing all different types of quantum computers, different types of quantum sensors to interoperate on the same network and using standard telecom fiber. We have other examples of that, such as quantum repeaters that are going to be needed to extend the distance of a quantum network if you're trying to go further distances between cities, for example. Those are the types of things that we're focused on, is building the best-in-class devices across the board so that you can build interoperable networks that serve a customer's need.
So at Xanadu, the real advantage we see of our approach is the inherent scalability of photonics, right? If you're already working in telecom wavelengths, it makes it a whole lot easier to network a bunch of modules together, right? So we see photonics as the simplest, most straightforward way to get the scalability, networkability, and modularity that you need to actually build out large-scale, huge data center size systems. Now, in terms of interoperating with other modalities, I think the key is going to be on the software side. You really want software frameworks, compilation frameworks that are adaptive, that can work on multiple different modalities of hardware, because you really do need lots of people developing software and applications that can run on top of these machines, right? That is something that we all benefit from collectively if we're all working towards that same goal of making useful and valuable applications available to industry. So, we think that the scaling piece really is about manufacturing at scale, improving component performance, and just getting all of the huge infrastructure together to make it happen.
So I'm going to press on that a little bit just to make it a little bit more exciting. The reason I'm going to press on that is, of course, the scalability you're describing is scalability within one particular modality. And obviously, from your point of view, you can connect photonics, computer with, let's call it conventional. It's not conventional, nothing is conventional in quantum, but with our optical, the stuff that the Kelsey is doing. So that's great because that's scaling up in one modality, to reach, scale for our correction for whatever. But when we're talking about interoperability with, let's say, I'll take trapped ions, which is not the most difficult, other modality. We don't have a superconducting qubit representative here, so we're not going to go into hot water. But nevertheless, what will be, and actually, so let me expand that. What will be the challenge then, to achieve this interoperability, not just on the software stack, incorporating all the different, versions of what quantum computation, quantum sensing, et cetera, can be, but truly exchanging information. What are the challenges? So let's start with you, Jordan.
And you mean between different modalities
Exactly.
of quantum computers
Exactly.
specifically? So look, I think the most interesting challenge here probably is a business challenge, not necessarily a technical challenge. I mentioned the technical challenge, which has to do with, do you have the right hardware and software to allow for interoperability? Quantum memories are part of that, like what Kelsey's working on. Quantum frequency converters we mentioned. It's the business challenge as well, which is getting these companies to come up with the right standards for interoperability, the right settings for interoperability. So is there a location that you can congregate and work on the same quantum network together and work on algorithms together? And I do think we're at an exciting moment in the industry where you have companies who are making significant progress every day. You have serious customers who are looking to buy from those companies. And probably the most evident place where we're seeing collaboration today is between hybrid algorithms with quantum and classical computers. Virtually every quantum application that folks are talking about today that's having commercial impact involves quantum and classical working in tandem and handing the most difficult tasks over to the quantum computer and handing back the results to the classical computer. So that's an example of where we're seeing a lot of great collaboration today. It's going to take more of that to tie all of the different quantum devices together and figuring out the right business opportunities to do so.
Thank you. Kelsey?
Yeah, so I think my dream for Photon Q is that we'd be working with all big quantum computing companies in the future. And I think Photon Q fits in two main areas for that. The first one would be multiplexing, whether it's probabilistic sources, if it's photon sources. But then also the big one is the networking aspect of it. And there's always going to be that synchronization challenge when you're networking these different qubit modalities. And I think that's where Photon Q fits in. And we'd love to be a part of every part of that ecosystem, connecting all those different qubit modalities.
Okay, so since Jordan mentioned, cooperation, collaboration, et cetera, this is a very good point. For sure, scaling quantum technologies requires collaboration not across companies, but laboratories, academia, the whole ecosystem. So from your experience, from your involvement, what are some examples of useful collaborations? What are some gaps we have of collaborations that we should be pursuing, but somehow we can't, or there are obstacles, or So let's see. I've been trying to randomize but you're only 3 and I forgot, so my memory is not very good. Okay, we'll start with you again, Jonah.
Happy to. So I'll say right here, we've got a great collaboration with IonQ on developing our software Penny Lane. We've got a plugin that directly connects to IonQ machines. If you want to run a program on an IonQ machine, you can set up a Penny Lane account and do that directly. We've got that with a number of the leading vendors of QPUs in the US and around the world. So, on the software side, again, I think that is an area where collaboration is generally easy. You don't run into too many IP concerns, right? The interoperability of heterogeneous hardware architectures is really challenging and maybe premature. I think it's important to study and understand where there may be advantage gains from mixing and matching different approaches. But I often say, let's master one before we start trying to integrate multiple modalities at the same time. On some of these new centers that are being stood up for algorithms development, software development, compilation, error correction, right? Those are all areas that, again, working together, these are advancements that benefit everyone, right? And they are things that push the industry ahead without necessarily setting any particular company back. So it's a lot harder on the hardware side to collaborate in that way. It can happen, but on the software and sort of all of the other higher levels of the stack, that's where I think you're going to see a real impact.
I agree with Jonah on a lot of the technical implementation here on the hardware and the software. From just an ecosystem perspective, it certainly is about more than the companies themselves. It's like you mentioned about the government labs, about the universities, and so I think you're going to see a lot more of that. Where do I look for inspiration on things that are already happening there? Take, for example, where we're based here in Chicago today with CQE, with the Chicago Quantum Exchange, is bringing together the local laboratories of Argonne and Fermi, the local universities, and companies to work together. And that's a spirit that we need to continue to capture. I also look at the QEDC, the Quantum Economic Development Consortium. That's a way in which we're all collaborating as an industry to push forward our standards and our government initiatives as well. So these are the areas that we need to make sure that as an industry we're continuing to stay tight on, because they will define what the industry looks like a few years from now. And we want to make sure that everyone's on the same page about what the technology needs to be, what the standards need to be, what the certifications are that will allow us to deliver a trustworthy enterprise product at scale and repeatedly. I think we are creating the right forums. We have a lot of the right forums today, and I'm seeing more and more of them sprout up across the country and across the globe, which is very exciting for what's next for quantum.
But yeah, I really appreciate you bringing up ecosystem in this conversation because I think it was a key thing for Photon Q's success. Just a quick snippet of how Photon Q started. Essentially, our CEO did his PhD on the core technology, and he was at a conference, and people were asking him, when can I buy this? And he was just like, oh, this is my PhD work. I'm not selling this, right? And then from there, actually, we got into the Duality Accelerator program, and that's really what kicked things off for us. It gave us that ecosystem to really be a part of and start networking with people, and really helped us develop a business as researchers, which we had no really experience with. So it really kicked us off, and I think we definitely should keep those kind of ecosystems for early stage startups.
So thank you, guys. So you covered, I should say, things that have gone well, although, Jordan, you did mention things that we need to do better, such as standards, et cetera, et cetera. What is the most important thing that we should be improving, out of a list? And I understand, we are in the beginning, right? But, what from your point of view is the most important thing? And I bet, it will be different for Kelsey than it is for you guys, but let's, so starting with you, Jordan.
I can say that. 2 words: government support. And I say that not just for the US government, but I say that for other governments as well. You have countries around the globe who want to remain competitive in quantum. And so those countries, those state and local federal institutions need to continue to support this critical technology. And we're seeing some great starts to that across the globe. We're seeing some great starts to that in the US, specifically looking at Illinois as a great example of how to do it right. But there's a lot more work to be done. And I think, if we care about this technology and the impact on society, which I think all of us in this room agree is going to be massive, we need to have the proper support, and that doesn't get done alone in a vacuum.
Good. Kelsey, let's go with you next.
Yeah, I think government support plays a key point in our decision as an early stage startup on where we're going to settle, right? And that's kind of still an open question. I think Chicago has been a great ecosystem for us, but there are also a lot of opportunities elsewhere. And I do hope there's potential for future collaborations with other ecosystems like Chicago, Colorado, New Mexico, to make it more of a statewide thing. I think that would be awesome. But yeah, I think government support really leads the decision on where an early stage startup is going to go, and more government support is better.
Jonah?
Yeah, agree 100% with government support. I would also add supply chains and manufacturing capability, right? These machines are going to need a lot of highly specialized components that are going to need to be churned out by thousands to the millions. And the question that we have is, do we have the infrastructure today to make that happen? I would say that depending on the modality, more or less, but as a fledgling industry, we are often at the back of the line when it comes to large-scale manufacturing, right? Because we just aren't going to make the same, at least today, the same sort of order volumes that established electronics companies do, right? And so thinking about what is the manufacturing and supply chain going to look like 5-10 years down the road, and starting to prepare for that. Because if we're not there, even if the technology is at the maturity that's ready for prime time, if you can't build fast enough, you fall behind.
That's actually, so I was wrong, I have to admit. I thought you guys will have at least between the startup and the other two, we will have different, pain points. But government support is a cross-cutting pain point, so I was wrong. But you touched on a very interesting thing. So there is the scaling up of the components we need, the manufacturing, and that is, a national lab has better scalability capabilities than an academic institution. probably better scalability capabilities than a startup, than a mid, way startup. Maybe not, compared to, an established quantum computing company. So there is a gap because, usually what you will do as a research entity, and I speak since we don't have another person representing labs, so I will jump in now, not as the moderator, but as a national lab representative. Usually national labs fill this gap, but what is needed, for what we're talking about to scale, our quantum infrastructure to achieve, greatness in applications goes beyond what national labs can provide. I mean, we can bridge the gap between an academic, idea, development, prototype, to bring it closer to, what will be a full-blown, checked, understood, et cetera, process for a fab. But, we can't produce it. So that's an excellent point. All right, so since we're starting to get a little bit more technical, let me throw something in that, it's now very, very in these days, AI. So obviously, I mean, quantum and AI are both in the category of supported, as is microelectronics, by the way, emerging technologies. But, control and error correction are essential for every quantum platform. They're also different depending on the platform you're dealing with. So could smarter control systems assisted by AI or, designed by AI, could be accelerating our success? What are your thoughts? I mean, how well are we doing incorporating AI to what we're doing in quantum at large and in quantum networking specifically and in scaling things up? We'll change. Start with Kelsey. Okay.
Yeah, so I would say for Photon Q, we haven't really been focusing on AI much. Been mostly focusing on working with photonic quantum computing companies, and maybe I'd throw it off to you to answer that question. Yeah, I think that's what I'll do.
But I mean, before we pass it on to the, so are you limited though in your conventional approach into looking at your controls, or you're not at the level yet that you think you need to to be better in optimizing things?
Yeah, so I do see some optimization problems that we have in our system that could be improved by AI. And I guess that's just a matter of seeing how the AI grows along with our growth, and seeing where we can tie that in. But really in the optimization of putting lenses in our system, it's actually not a trivial problem. It sounds like a trivial problem with just putting lenses and doing Gaussian beam optimization in our system, but it becomes difficult when you have a constrained space and you're trying to design around that, and you need to have focusing points at certain points. So I could see that being an interesting optimization problem that AI could play into.
So are we limited? Absolutely not. I think there's a lot of opportunity, though, to continue to improve things using AI. Though I think one of the most obvious things that AI contributes to quantum is actually not on improving our control systems. It's on demonstrating the opportunity for quantum out there, especially on the quantum algorithm side for quantum computers. And what I mean by that is we've demonstrated as society that we have this voracious appetite for AI. That's been clear, if nothing else, over the last few years. And we've also demonstrated the downfalls of the amount of capital that needs to be invested, the amount of space it takes up to build data centers, the amount of energy that's required to power those data centers. And we're left wanting for more. We want better AI, stronger AI, faster AI, and the support to do that. And I think that's what quantum's going to contribute. So of course, there's a relationship of AI continuing to contribute to quantum. There's also the reciprocal relationship of quantum contributing to AI. And I'm thrilled that we're a part of that. It's what I view as a very virtuous cycle.
Jonah?
Yeah, I'd agree with both those points. I'll just say, we certainly bring AI tools into our R&D process. It's helpful for optimization, for simulation, for supplementing our experimental work. We use every tool available to us to improve the components to the highest degree. But I think Jordan's point is right, that AI as an industry is actually probably more instructive than actually AI tools themselves for the development of the industry. You see the importance of the semiconductor industry. You see how much capital is required, how much energy is required, how much water, right? These are all things that you can learn from when thinking about the future of quantum computing. Maybe make fewer mistakes, not repeat the same mistakes that maybe some of the AI industry has made, and just sort of see how they can complement each other as both technologies develop in parallel and together.
Good. So let's look in the future a little bit. So thinking ahead 5 and 10 years, what do you think a scaled quantum network connecting quantum resources will look like? So yeah, starting with you.
Me?
I think I started with you before, so
Okay.
now, yeah. Again, I'm trying to remember. I'm an old man. I don't remember, so I think it's Jordan.
Happy to pass off. Okay. What does a quantum network look like in 5, 10 years? The first thing to know is that there will be a lot more of them, and we should be prepared for that. Today, out in the world, there are 40 plus quantum networks. That's significant as is. I think most people would be surprised to hear that there are 40, that there are dozens of them. But I think you're going to see many, many more in 5 to 10 years, or you might say they're all part of one global network, and so it collapses down, right? So the first thing is expect more ubiquity, and for us at IonQ, the way that we're trying to accomplish that is first, we're focused on quantum networks on the ground through commercial fiber, of which we have many deployed with customers in live commercial use cases today, and of which we're proposing and building many more. The second thing that we're doing is we're taking those quantum networks into space. And we have satellite capability as a company to continue taking quantum devices and launching them into orbit so that you're not bound only to fiber on the ground today. That means if I want to connect from here in Chicago to the UK, I don't need to thread a fiber under the water. I can do that via free space optics with a satellite. So those are the types of things that we're seeing. So if the first concept is that there will be more quantum networks. The second is that they'll be more and more global. And the third is that they'll be at scale with devices that scale. So think about every quantum device you might know today will be smaller and cheaper and way less and will be much more robust. And that's what we're focused on. The nice thing at IonQ is we have the people and the capital to continue pushing the envelope forward every single year and iterating on these devices, such that they're achieving those size, weight, and power goals consistently. So, and I think that means that you have quantum networks in the future that are more ubiquitous, global, and also embedded into every enterprise and government institution, just embedded worldwide.
Jonah?
Easy answer is it depends. I think part of it is going to be how much early adoption do we see from those industries and government agencies that are going to be on the cutting edge, right? People in industry are looking for demand signals. They're looking for first movers. So if you see government agencies saying, yes, this is something that we think is essential to our success, if you see financial institutions, aerospace companies saying, yeah, this is something that really is improving our products, making things more secure, improving our workflows, then I think it's gonna, you're gonna see the trend lines go up very quickly. So a lot of that's gonna depend on what kind of signals we get from those first movers. And I think we're seeing a lot of promising signs today. And so I anticipate that we're gonna, like Jordan said, just have a lot more and a lot more embedded in key commercial and government systems.
Kelsey?
Great. Yeah, so I think the future quantum network is going to be composed of different platforms, and you guys brought up some good different platforms, whether that's fiber or that's space or that's drone to drone, which my advisor likes to do. But close to my heart is definitely the space applications. So outside of Photon Q, I worked on the Seek payload, which is an entanglement source that's on the International Space Station. And I'll give a shout out that we're actually doing a live demonstration with it after the poster session. So keep an eye out for that, and scan the QR code to play a game that is incorporated with that live demonstration during the poster session. But yeah, I think there's going to be a lot more activity in the space quantum networking area. Just this year, I know there's going to be a bunch of new launches. I was just at a QNew conference, which was networking, but there was it was in Europe. But there's a lot of planned launches happening right now. So I think space is going to become more and more of a build area for quantum networking, which I think is super exciting. But there's also a lot of challenges that come with it. I think for PhotonQ, it'll be interesting to follow that progress, and we're going to need quantum memories, whether it's on a quantum computer on the ground, whether it's networking with fiber, or whether it's networking in space. So we're definitely going to work towards also being in that space. My big dream, my big goal would be to actually do a demonstration with one of our memories in space, but there's a lot of engineering challenges that come with that, and I think still a lot of work to do.
So you're bringing a very interesting point. Actually, all of you did, but it's good that we ended up with you, because at the end, you know, if you want to say that your end state is to have the ability, as Jordan, you know, made an example, you know, talk to the UK, you have to use a satellite to talk to the UK. So, and you mentioned, Kelsey, that, you know, there are engineering challenges. So in addition to what both Jonah and Jordan talked about in terms of, you know, embedded miniaturization, et cetera, you need to make your equipment payload capable, because you have to launch it. So focusing on that, I mean, is that behind everything else? I mean, you know, what's the current state of you know, affairs in launching you know, full systems to space?
Yeah, so essentially there are two main issues when you're launching an optical system into space. And the first one I would say is you're launching on a rocket, so it's going to vibrate a lot. Mm-hmm. And these are optical systems that need to be coupled into a single mode fiber after hundreds of reflections. So there is a challenge there in keeping it robust enough for launch. And there could be work towards maybe after launch alignment systems that can happen once it's in space. But then also I would say the temperature is a big problem once you're in space, right? You're experiencing a lot of temperature fluctuations, and that's what we had to deal with our optical system that's on the ISS. But also power constraints. It's very expensive to send things to space, and you have to have power considerations once you're on like a free flyer satellite. So it's a much different game once you're going to space.
So for this ability to sustain the acceleration of the rocket, miniaturization, putting everything on a chip, presumably is something that, you know, is highly desirable, correct?
Yeah, making systems as compact as possible. Recently in the aerospace world, CubeSats have become extremely popular now, and it's very easy to purchase one. It's just designing systems that fit in those CubeSats that's the challenge within those power constraints, right? Yeah.
Yeah, that's actually interesting, because it links back to the conversation we had about supply chain, because when you reach the point that you have something that you think might, you know, make it, then you have to build it, and you have to build it at enough scale that is appropriate for what you're doing to launch, which is, you know, not a tremendous scale that your, you know, cell phone, you know, components. So anyway, so that's also a challenge.
Yeah, and the last thing I will say, like, the similar challenges, I mean, I think launching it to a rocket is exponentially higher challenge, but there's similar challenges to having deployable systems, which is what we want to have at PhotonQ for our memories, is to have it as a rack-mountable system. And same thing with that, like delivering those systems, you're going to have some vibrations in the delivery, potentially temperature fluctuations during that process. So it is one step, it is still working on the same engineering problems, but I would say space is obviously a lot bigger challenge.
It's also the ultimate test environment because of the constraints from the environment, right? The companies that can invest in space rating their technology today will have a major advantage in the future. And it might sound early to critics that you're investing in space while we're still so nascent as an industry, But the reality is the industry is very rapidly crystallizing and firming up. And I think you would have had naysayers years ago tell IonQ that we were early to invest in manufacturing. But guess what? That's what's brought down our time to delivery. It's what has allowed us to support all 3 public clouds today. AWS and Google Cloud and Azure consistently. And so these investments early in the platform go a long way in making sure that the company has long-term advantage.
Excellent points. Thank you. So I am going to ask one last question, and then we will open it up to questions from the audience. And I was told by my co-panelists that we need to finish exactly on time and maybe a couple of minutes before, because some of them actually have to do things at a poster session. So my last question, and then we will open it up for maybe 10 minutes of questions from the audience. So my last question is, how will a functioning quantum network change the economics in the quantum ecosystem? I mean, how important that is to go to generate revenue beyond the investment? Jonah.
I mean, I guess it depends on what you mean by a quantum network. Clearly, you are going to need to network together lots of diverse heterogeneous systems efficiently and in a way that increases the utility of all of them, right? That's the thing with networks, right? That the benefit of the internet was that you were able to connect diverse systems and share resources and move information around quickly. And the same is true with quantum systems. So the key is going to be, can we do that in an economically viable way? Can we do that in a way that makes money for those organizations and companies that invest, right? And does it provide utility to the institutions that use them? So that's it.
I'd say there are 3 key ways that quantum networks will impact the economics of the industry and totally change the game for the quantum business. The first is that you're going to have a broader suite of very powerful applications that you can achieve. Because quantum networks, the same technology, is what allows you to link computers across broad distances, but also cluster computers together to get more and more scale out of your quantum systems. It's basically always been IonQ's approach to scale, is that in addition to increasing the number of qubits on a single computer, we can connect multiple computers and tackle larger and larger problems, just like you do in clustering with classical computers today. So that's one, is just bigger problems. The second is more diverse problems, which is the interoperability, again, of different quantum devices onto a network, whether that be quantum computers of different modalities, photonics, superconducting, trapped ion, neutral atom, perhaps. And so that's a broader, more diverse set of use cases, and even devices like quantum sensors hopping onto the network that can solve new types of problems. And then the last is security, which we haven't talked a ton about today, but quantum networks are the way that we'll be able to transmit quantum secure information. Using a quantum network is the only information theoretically secure approach to transmitting information. So the only way that you can guarantee that your information is going to be protected from a quantum attack, and also has benefits for today's cyber attacks. So if you think about power, diversity of problem, and then security of the problem, those massively change the game for the economics here.
Great. Yeah, I think Jordan did a good job of explaining all the technical benefits, but maybe I'll take a different approach and say, previously I talked about all these different communities like Chicago, Colorado, and New Mexico that are building these quantum hubs, and I think a future network will really be able to finally connect those and foster those collaborations that we talked about, that we said would benefit the ecosystem as a whole, to like finally start connecting potentially different platforms. I know there's challenges with that too, but finally start really connecting all these different hubs, industry, national labs across the country.
Thank you. So, questions from the audience?
First off, I want to thank you all for a wonderful panel. You did a great job. I think we all know and you touched on it with optical engineering and algorithm development, et cetera, that if we're going to scale, we need to develop the talent pipeline beyond physics PhDs. And so I kind of want to know from an industry perspective, what would you like to see from institutes of higher education invest in their quantum workforce development? Or in other words, what programs or integration of program types are you most interested in seeing deepen their quantum pedagogical footprint?
Okay, here, Jordan, start.
I'm happy to take that. So I think we've done well in two ways. One is we have a lot of excellent physicists, and we've been able to attract a lot of those people to companies in the space. IonQ is very proud of our workforce that we've attracted. The second thing is, as you mentioned, there's a diversity of engineering disciplines required to make a quantum device work, right? Quantum computer work, quantum network work. And that's been very helpful to overcome the workforce development challenge, is that we just as equally need a physicist as we do a mechanical engineer, a software engineer, an optical engineer, and those exist latently in the world today because we've been training those for other industries. And the experience, the different perspectives that they bring to the quantum space is actually very refreshing. It's not just a room of all physicists anymore. These are real companies at scale. What I'd love to see pedagogically with universities is more specific quantum curriculum that bridges the gap and that's truly integrated in terms of I want that mechanical engineering student understanding how their work would apply to a quantum computer, or I want that electrical engineer to study networking from a quantum perspective. And those courses I see blossoming starting to bud today and not quite blossomed, right? We're just kind of at the early stages of having universities roll out broader quantum curricula.
Yeah, I would just echo the interdisciplinary studies, right? The quantum computing is really cool because it does integrate so many diverse fields of study into technology, right? You need somebody who's versed in computer science, electrical engineering, physics, materials science, right? Chemistry. You really need a diverse and unique set of expertise to work in this field. And so the more you can have programs that consciously do that, the better. From an industry side, I think if I had my way, I would say significantly more attention to quantum computing applications. Right? There's a lot of great work happening on building the hardware. I think we need as much work happening in parallel to develop the applications and use cases. We need to be able to do useful, valuable things with these machines when they're available. And the more smart people we have looking at the problems, exploring what quantum computers are really good at, what quantum networks are good at, what are the security vulnerabilities, the better for everybody.
Kelsey?
Yeah, so I think in my career, my PhD has been a little bit different than I would say a typical physicist PhD, in that I was very engineering focused, trying to make the system work in space. And I think there could be more support for projects like that, like actual demonstrations of putting things, optical systems that we understand pretty much the physics of it, but when you put it in a different environment, it's a whole different ballgame, and learning how to operate these systems. So I think more of a push to get students involved in those kind of projects, more demonstrations, and that's how we learn and grow and actually tackle those issues to actually deploy quantum networks like that.
Thank you. Other questions? It's in the front.
First of all, amazing panel. I have learned a lot. And speaking about quantum network in space, Chelsea, you mentioned, Kelsey, sorry, you mentioned that would be great actually connecting quantum hubs, especially, well, in the US, but how about internationally? So I did hear that you connect to UK as well. So do you see that, well, I suppose Jordan and Kelsey and I'm sorry.
Jonah.
So there you go. The quantum network space-wise being further into connecting hubs internationally, and what would be the applications of that to advance quantum as a whole, right? Wouldn't that be a leapfrog to it?
So I think definitely the space application is intended to reach international and domestic use, but international is one of the key use cases. And what do we envision, for example, as kind of early use cases there? Well, I think right now you're going to have there's not going to be a homogeneous rollout of quantum worldwide. And so if we want to improve access to quantum computers, that's probably one of the first ways that we can do it, is by having linkages to the best quantum computers in a certain country and making them accessible as part of global diplomacy and global collaboration on the technology. That's probably one of the first ways we can think about it, but also think about secure communication across a global landscape where allies are trying to communicate on various actions. It's a key area where I think countries will be keen to collaborate in space.
Jonah, Kelsey, to add?
Sorry, so we got a
Kelsey?
follow-on question, or?
Actually, if you don't mind, I will add. I mean, I think I will order them as security first because that will be easier, and then accessing quantum computers across the globe, just based on rates and the value, if you wish, added to doing that.
The reason I was asking that is because I'm supporting Brazil to develop their hub, and there is already a lot of interest, especially on oil and gas, mining, and finance. So I'll be talking to to you guys soon.
Okay. All right. There is another one.
Good afternoon. Thanks for sharing this, your expertise. I want to build upon the question earlier in terms of the talent pipeline beyond the PhD physicists. Thinking about community colleges and high school students, what would you suggest in terms of making sure that we broaden access and we really build the talent pipeline so that we don't have a bottleneck with all the demands of all this coming together in a global race?
Kelsey, go ahead.
Yeah, great question. I think for Photon Q, since our systems are optical, and I wouldn't say they need a PhD expertise to build them, at least. Maybe designing them is a different story, but just to build the quantity of these, I don't think you need a higher degree. And so I think students, high school students and early career college students can play a role in this, but I think they need to be exposed more to hands-on optical systems and actually building them. That's really the experience we need. And so time in a lab, if you can offer high school students this through learning experiences, but actually getting that hands-on experience and building those optical systems, I think would be good.
Yeah, I would just say generally getting young people excited about STEM, right? This is still a very cutting edge field, and I think it will be driven for the foreseeable future by PhD physicists, computer scientists, electrical engineers. But you need to get those young people excited in high school, and when they're fresh out of high school, get them excited about these topics so that they say, yeah, this is something really cool that I can, devote my academic and professional life to. So what I would say is getting those people exposure to these technologies, like Kelsey said, bring them to a lab, show them how cool some of this equipment is, how you can have a really fulfilling, exciting career long into life, and that to do that, you really need to buckle down and learn, the science and math to get you there.
I'll share my personal experience here, which is of growing up in Chicago as a kid, which is probably the reason I'm on the stage today, is I started engaging with quantum physics in high school. And we had a small group of us, the nerds in the class, who were in our high energy particle physics class. And I had a brilliant physics teacher who saw this as an opportunity for us to learn, brought us together for lectures during lunch during the week, And importantly, we visited our national labs here. So we made trips to Fermi and to Argonne. And for our group, that was all the difference of understanding that physics could be a part of our lives and our career, that there was a life to build at the intersection of engineering and science and society. And that's what we need to continue doing. And bring it full circle, that same guy who was running the particle physics club in high school gets to be here in his home state talking about quantum physics on a stage and doing this professionally. And there's no substitute for that in our education system today.
I would like to add, again, we're going to close after that. I mean, for high school, as you just heard from Jordan, I mean, you need the resources to have teachers that are knowledgeable enough to excite the students. And then, resources to organize the visits to the national labs, et cetera, et cetera. So high schools need to have set resources. And I'm very far removed from high school, so I can't really tell you how you acquire that. Now, for community colleges, which was the second part of your question, that's a very interesting thing, because you could have programs in community colleges that cover areas that are very, very, very important for quantum. For example, cryogenics. I mean, things that you don't need to have a PhD to actually be involved and engaged in the workforce of all that. So anyway, I mean, tailoring the programs of the community colleges looking into these technologies is again something that maybe within the resources they have, they can do. Okay, so actually I said I want to finish 2 minutes early, and I managed to not do that. We went to the whole thing. So thank you so much for sharing your perspective with us, and thank you, the audience, for your participation. And
Thank you. What a great panel, ladies and gentlemen.